Secondarily, let's ask if there's a potential for the forces that act on a wing that can both pitch and plunge. Now, plunge means it can move up and down in this z coordinate direction. And so now the two coordinates alpha and z enter, and this lift force gives rise to both a vertical force acting on z as well as a moment acting on alpha. And so you have a more complicated problem. So there will be two answers in this problem. One for the left case, it's a single degree of freedom. One for the right case, that's a 2 degree of freedom system. We'll start with the single degree of freedom wing. Here the relevant force is the moment, and that will be some distance epsilon between the center of lift and the pivot point, and then the lift itself. So epsilon is a constant, and then you have the coefficient of lift times q times s times the angle of attack. And the real proof of the pudding here is, does there exist a work potential as a function of alpha such that you can recover the moment as minus the gradient of that work potential? So you have to guess this in a sense. How can we recover the moment up here by taking a derivative? Well, when you see that this is linear in alpha, you realize, gee, if I just doctor up a quadratic potential with alpha squared in it, and then I may have to put the minus 1/2 in here to account for the minus here, and then the variation here, or the derivative. Let's see if this works. You take a derivative then, minus a derivative of that quantity, and the minuses cancel here. When you do the derivative on alpha squared, you're going to get 2 alpha out of it, and the 2's are going to cancel, and lo and behold, you can come up with such a moment. So it's a two-step. It's like you transform into a work potential, and then you transform back to the moment, and that's a two-way street. If you know one, you know the other. That's the classical work potential. Now let's look at the 2 degree of freedom wing and see what happens. This time we have both a moment about the center of interest there, often called the elastic axis in a flutter problem, and then the lift. And so a moment is going to primarily be the generalized force acting on the displacement alpha. Lift is the generalized force acting on the displacement z. And again, the question is, can you find a work potential such that when you take minus the gradient of the work potential, can you recover those two forces? Well, we have an expression for the moment. The moment was related to the epsilon distance times the CL alpha QS alpha. And the question then, if you try to invert this relation rather than a differential relation as we have it, suppose you try to do indefinite integration on these two relations one at a time. So to recover the work potential from the upper equation, you have to do indefinite integration on alpha, which we do here, leading to the alpha squared term, plus a constant of integration, which in fact is an arbitrary function of z, which is the coordinate not being integrated at the moment. Then you look at the second equation and do the same thing, and the question is, can you integrate the lift? Well, the lift is the dCl d alpha times qs alpha, and you integrate it on z this time, and you'll get an alpha z behavior plus an arbitrary function of alpha. So now you really have two conditions that must hold simultaneously, because we've got to be able to map from the right here, from the work potential to the left, and so they must simultaneously hold. So let's see if we can equate these two versions of the work potential, and when we size them up, we have a quadratic term alpha squared on the left with an arbitrary function of z. We have another quadratic but a mixed term alpha z here, plus an arbitrary function of alpha, and there's no way you can get that to balance out. You just can't do it, and it's primarily this alpha z term. There's no way to balance it here with a quadratic and with a function of z only. So the answer is those cannot be equated. There is no work potential. The expressions are not integrable. So that will end our problem session.